Hi, welcome to our channel Nano Raj Tech. Today we discuss about Introduction to Machine Learning in Mechanical Engineering. Hope you are enjoy. Please like, share and subscribe our channel Nano Raj Tech. Here we discuss about first one overview of different forms of learning used in machine learning for intelligent systems in mechanical engineering. Second one overview of different forms of learning in mechanical engineering. Next one machine learning for intelligent systems, overview of different forms of learning. Let us we start. First we discuss overview of different forms of learning used in machine learning for intelligent systems in mechanical engineering. Here's an overview of different forms of learning used in machine learning for intelligent systems in mechanical engineering. Supervised learning. Definition: a learning approach where the model is trained using labeled data, input-output pairs. Applications in mechanical engineering. Predictive maintenance, where predictive maintenance is a maintenance strategy that uses data analysis to anticipate equipment failures and schedule maintenance only when needed, optimizing resource allocation and minimizing downtime. It combines condition monitoring techniques with machine learning to predict potential problems before they occur, allowing for proactive intervention rather than reactive fixes, e.g., estimating component lifespan based on sensor data. Quality control and defect detection in manufacturing processes is explained by quality control, QC, and defect detection are crucial in manufacturing for ensuring products meet specified standards, minimizing waste, and enhancing customer satisfaction. Implementing robust QC processes reduces defects, improves efficiency, and helps maintain brand reputation. System performance optimization through historical data analysis. Where system performance optimization using historical data involves analyzing past system behavior to identify patterns, bottlenecks, and areas for improvement, ultimately leading to enhanced efficiency and reliability. This approach leverages statistical analysis, data mining techniques, and performance monitoring tools to pinpoint issues and implement targeted optimizations. Common algorithms. First, linear regression. Linear regression is a supervised machine learning algorithm that learns the relationship between independent and dependent variables by finding a linear equation that best fits the data. This best fit line minimizes the difference between predicted and actual values. It's used for predicting continuous numerical values. Next, support vector machines, SVM. Support vector machines, SVMs, are supervised machine learning algorithms used for classification and regression. SVMs work by finding the optimal hyperplane that best separates data points into different classes. This hyperplane is chosen to maximize the margin, which is the distance between the hyperplane and the closest data points, support vectors, of each class. SVMs are particularly effective for high-dimensional data and can handle nonlinear data using kernel functions. Next, neural networks. Neural networks are a core component of artificial intelligence, AI, and deep learning, inspired by the structure and function of the human brain. They are essentially a computational model composed of interconnected nodes, neurons, organized in layers, which process and analyze data to perform tasks like image recognition, natural language processing, and more. Next, decision trees. A decision tree in AI is a flowchart-like structure used for both classification and regression tasks. It's a supervised learning algorithm that makes decisions based on a series of rules learned from data. These rules are organized into a tree-like structure, with nodes representing decisions and branches representing the outcomes of those decisions. Second one, unsupervised learning. Definition: the model learns patterns and relationships in unlabeled data without predefined outputs. Applications in mechanical engineering. Anomaly detection in machine operations, where anomaly detection is the process of identifying data points, events, or observations that deviate significantly from the expected or normal behavior. It's essentially about spotting outliers or unusual patterns within a dataset. These anomalies can be rare occurrences or inconsistencies that stand out from the majority of the data. It's essentially about spotting outliers or unusual patterns within a dataset. These anomalies can be rare occurrences or inconsistencies that stand out from the majority of the data. Clustering of operational states for pattern recognition. Clustering is a fundamental unsupervised machine learning technique where data points are grouped based on their similarity. In the context of operational states, this means grouping similar operating conditions or behaviors of a system. For example, in a manufacturing plant, clustering could be used to identify different operational modes of a machine, such as normal operation, maintenance mode, or error states. Elaboration is: clustering operational states involves grouping similar operational behaviors or patterns into clusters using unsupervised machine learning techniques. This process is valuable for pattern recognition in AI by identifying distinct operational modes and anomalies. Popular clustering methods include k-means, hierarchical clustering, and Gaussian mixture models, each with strengths in handling different data characteristics. Dimensionality reduction for complex system analysis. This is a fundamental technique for analyzing complex systems by transforming high-dimensional data into a lower-dimensional representation while preserving its essential features. It improves computational efficiency, reduces noise, enhances data visualization, and supports more accurate machine learning models. In engineering applications, dimensionality reduction enables faster decision-making, better pattern recognition, and more effective analysis of complex mechanical systems, contributing to the development of intelligent and data-driven solutions. Common algorithms. K-means clustering. K-means clustering is a popular unsupervised machine learning algorithm used to group data points into K-clusters based on similarity. It aims to minimize the variance within each cluster while maximizing the separation between clusters. Principal component analysis (PCA) is Principal component analysis (PCA) is a dimensionality reduction technique used in machine learning and data analysis to transform a dataset into a new set of uncorrelated variables called principal components. These components are ordered by the amount of variance they explain, with the first component capturing the most variance, followed by the second, and so on. PCA is often used to simplify complex datasets, improve computational efficiency of machine learning algorithms, and aid in data visualization. Autoencoders. Autoencoders are a type of artificial neural network used in unsupervised learning for tasks like dimensionality reduction and feature learning. They work by encoding input data into a lower dimensional representation, latent space, and then decoding it back to reconstruct the original data. This process allows autoencoders to learn efficient data representations and discover hidden patterns in unlabeled data. Third one, semi-supervised learning. Definition: a combination of supervised and unsupervised learning, utilizing a small amount of labeled data along with a larger set of unlabeled data. Applications in mechanical engineering. Fault diagnosis with limited labeled failure data. Fault diagnosis with limited labeled data is a challenge in many real-world applications. To address this, researchers are exploring methods that leverage unlabeled data or generate synthetic data to augment the limited labeled samples. Techniques include semi-supervised learning, self-supervised learning, transfer learning, and data augmentation strategies. These approaches aim to improve model accuracy and robustness when labeled data is scarce. Material property estimation with sparse experimental data. AI can be used to estimate material properties even with limited experimental data, using techniques like machine learning and domain adaptation. These methods allow for the prediction of properties for new materials by learning from existing data, even when the data is sparse or incomplete. Reducing labeling costs in production lines. To reduce labeling costs in AI production lines, techniques like active learning, leveraging pre-trained models, and using third-party data labeling services can be employed. These methods aim to minimize the number of labeled data points required for training, thereby reducing the associated costs. Common algorithms. Self-training, self-learning AI, or autonomous or unsupervised learning AI, refers to artificial intelligence systems that can learn and improve from data without explicit human intervention. Self-learning AI has significant applications in cybersecurity in identifying and combating potential threats. Graph-based models. Graph-based models in AI represent data as interconnected nodes and edges, enabling the modeling of complex relationships and dependencies. These models, particularly graph neural networks (GNNs), are crucial for tasks involving relational understanding, such as knowledge representation, network analysis, and semantic reasoning. Generative adversarial networks, GANs. Generative adversarial networks, GANs, are a type of machine learning model, specifically a deep learning architecture, used for generating new data instances that resemble the training data. They are composed of two neural networks, a generator and a discriminator, that compete with each other in a game to produce increasingly realistic data. Fourth one, reinforcement learning, RL. Definition. The model learns through interaction with an environment by receiving rewards or penalties based on actions taken. Applications in mechanical engineering. Autonomous control of robotic systems. Intelligent autonomous control systems use techniques from the field of artificial intelligence, AI, to achieve this autonomy. Such control systems evolve from conventional control systems by adding intelligent components, and their development requires interdisciplinary research, e.g., path planning for automated vehicles. Adaptive process control in manufacturing. AI-driven adaptive process control in manufacturing optimizes production efficiency, reduces waste, and improves product quality by dynamically adjusting process parameters based on real-time data and historical trends. This approach enables systems to compensate for variations in raw materials, equipment conditions, and other disturbances, leading to more robust and efficient manufacturing processes. Energy-efficient operation of mechanical systems. AI can significantly enhance the energy efficiency of mechanical systems through various methods, including predictive maintenance, optimizing system performance, and enabling smart grid integration. AI-powered systems can analyze data, predict potential issues, and adjust operations to minimize energy consumption while maintaining optimal performance. Common algorithms. Q-learning. Q-learning is a model-free reinforcement learning algorithm that enables an agent to learn optimal decision-making through trial and error interactions with its environment. By continuously updating Q values based on rewards, it identifies the best actions to maximize long-term performance without requiring prior knowledge of the system. In mechanical engineering and intelligent systems, Q-learning is widely applied to process optimization, robotic control, autonomous systems, and adaptive manufacturing, making it an effective approach for solving complex sequential decision-making problems. Deep Q networks, DQN. Deep Q networks, DQN, extend traditional Q-learning by combining reinforcement learning with deep neural networks, enabling intelligent agents to solve complex problems with large or high-dimensional state spaces. By approximating Q values using deep learning, DQN improves decision-making, learning efficiency, and adaptability in dynamic environments. In mechanical engineering, DQN is applied to robotics, autonomous control, predictive maintenance, process optimization, and smart manufacturing, contributing to the development of advanced intelligent systems capable of handling real-world engineering challenges. Policy gradient methods. Policy gradient methods are a class of reinforcement learning algorithms that learn optimal decision-making by directly optimizing the policy, which determines the probability of selecting actions in different states. Unlike value-based methods, they are well suited for continuous and high-dimensional action spaces, making them effective for complex control tasks. In mechanical engineering, policy gradient methods are widely used in robotics, autonomous systems, process control, energy management, and intelligent manufacturing, where they enable adaptive, stable, and efficient decision-making. Their ability to optimize long-term performance in dynamic environments makes them a key technique for developing advanced intelligent systems. Fifth one, deep learning, DL. Definition. A subset of machine learning using deep neural networks to model complex patterns and relationships in large datasets. Applications in mechanical engineering. Computer vision for defect detection using image processing. Predictive modeling for complex system behaviors. Intelligent fault diagnosis through vibration and sensor data analysis. Common architectures. Convolutional neural networks, CNNs, recurrent neural networks, RNNs, transformer models. Sixth one, transfer learning. Definition. Reusing pre-trained models from one domain and fine-tuning them for a related task. Applications in mechanical engineering. Adapting predictive maintenance models from similar machines. Accelerating design optimization processes. Using knowledge from simulated environments for real-world applications. Common techniques. Fine-tuning deep learning models, feature extraction. Seventh one, federated learning. Definition. A decentralized approach where models are trained across multiple devices while keeping data localized. Applications in mechanical engineering. Collaborative machine learning across distributed manufacturing units. Enhancing data privacy in industrial IoT systems. Predictive maintenance without centralizing sensitive machine data. Common frameworks. Google's federated learning, TensorFlow federated. By leveraging these different forms of learning, intelligent mechanical systems can achieve higher efficiency, reduced downtime, and improved decision-making capabilities in real-time industrial applications. Next part, we will discuss about machine learning for intelligent systems, overview of different forms of learning. So I think this video is more helpful for you. If you like, please comment, share and subscribe our channel Nano Raj Tech. Thanks for your presence. Thank you once again. We'll meet you next week.